This Mathcast will walk you through section 9.4 on polar curves. Chapter 9 is an interim chapter that reviews 4 topics from pre-calculus. These topics have not been revisited thus far in this text because they are part of the BC, not the AB course framework. The remaining chapters in this text will apply calculus to these concepts. Now, it is encouraged that all students complete Chapter 9 in entirety. However, be aware that this chapter will not introduce any new topics from calculus. So, if you are confident that your students have strong pre-calculus skills, you could consider skipping or picking and choosing from the sections in this chapter. Section 9.4 will explore polar curves, how to sketch them, how to rewrite polar functions in rectilinear form, and also how to recognize the parent forms of popular polar curves, such as circles, cardioids, and multi-petaled roses. Also, how their parameters will affect the shape of their graphs. This is to set the foundation for Chapter 11, where in Section 11.1, your students will use integrals to compute the area of regions contained by polar curves, and in Section 11.4, they will use derivatives to compute the slope of polar curves. Before starting Lesson 9.4.1, distribute a couple of copies of the Polar Graph Paper resource page to each student. They can use this resource page to sketch polar curves throughout this section. Now, the first problem in this lesson, problem 9-104, reviews polar coordinates. This is an important problem, but you do not want it to take up too much class time because the next problem, 9-105, is a long one. So consider using a study team strategy to speed things along with this opening problem. One way to do this is with a modified version of red light, green light, where the whole class will be participating in the red light, green light activity together. What can happen is the teacher, you, will read part A to the whole class and then give the green light and let the teams work on that until you call red light, finished or not. Then pull the class together and check their answers for part A, discuss them, and then move on to part B, again with this red light, green light cycle. Using this strategy, you will be able to have frequent opportunities to check for understanding while still leaving you ample time for the big activity to come. Problem 9-105 is the big problem. In this problem, your class will work together as one team to walk, so to speak, the 4 polar graphs listed in this problem parts A through D. Now, you're going to need materials for this activity, and some of these materials you're going to need to prepare in advance. For example, you're going to need marker tiles, like the ones shown here. Marker tiles should be solid objects that are each labeled with the angles of the unit circle 0 through 2 pi. They could be as heavy as children's blocks, Legos perhaps, or as light as index cards. They just need to be substantial enough that they are unlikely to blow away or to slide when laid down on the floor. You will also need a rope, and to prepare this rope, you're going to have to mark off or label or even knot 8 or 9 equal-sized intervals. And this rope, when stretched, is going to represent the radii of a polar grid. And when it is rotated about the pole, each of these markings will trace out a concentric circle, creating a polar grid. Now, it's hard to see here, but in this picture, each of the markings was made by a piece of tape, and each piece of tape was labeled with the numbers 0, 1, 2, 3, 4, 5, etc., and they're spaced 1 foot apart each. This will help your students to have the labeling on the rope. It'll help them keep track of the concentric rings. Just make sure that the 0 is marked, because that ultimately will be the location of the pole. This problem will start in the classroom and end out of the classroom, preferably outside somewhere where there is concrete on the ground that you can mark up with chalk. Now, in the classroom, hand out marker tiles so that every student, or every pair of students, depending on the size of your class, has been assigned a different value of theta, and then hand out index cards and have the students label their index cards with the angle they were given. This student was given 2 pi over 3. Next, on the index card, Ask the students to compute the corresponding r coordinate for each of the 4 polar functions a through d listed in problem 9-105. As you glance at their work, remind the class that radii of polar functions could be negative. Also, for this problem, if the r value happens to be an irrational number, tell them to write its approximate value in decimal form. Students will then take their completed index cards with them outside or into the hallway, depending on where you're doing the activity, and they will use these index cards as references for the rest of this activity. Now take your class outside. Preferably go somewhere where there is concrete that you are free to mark on with chalk. But if that is not possible, go into the hallway and, if you can, lay down a bunch of butcher paper and do the markings in pen or marker. Now, once situated, your students should start by looking on the ground for a line that could represent the line for theta equals 0, that radii on the polar grid. Now, this line could be drawn with chalk on the ground, but ideally, it would be a line that's already etched into the concrete. And once they identify that line, they should lay down their rope on it. Again, this line represents theta equals 0, that axis on the polar grid. Next, one student will hold intact the part of the rope that's labeled with the number 0. That'll be the location of the pole. And another student will have the job of rotating the other end of the rope, nice and taut, 360 degrees around that pole, and that will happen once the teacher says go. Now, here's how the walk will work. The teacher will call out the first polar function, which in part A is r equals 6. And the students at that point shout out together, standing in a circle around this grid, theta equals 0, because that's where the rope is at that moment, and the student who's holding the theta equals 0 marker will plot their marker in the correct location, which would be 6 units from the pole, because this first function is r equals 6. And then, with the rope pulled taut, the student holding the end will start rotating the radii slowly towards pi over 6. At that point, the entire class shouts out, theta equals pi over 6, and the student who was assigned pi over 6 will plot their marker. They are also plotting 6 units from the pole because, again, the function is r equals 6. And this process continues towards pi over 3. The student who was assigned pi over 3 will plot their marker, and we continue through all reference angles, 0 through 2 pi, and one after another in order, and everyone will wait their turn for the string to reach their assigned reference angle, and their angle will be called out before they plot their marker on their coordinate point. So in the end, once all the markers are plotted, students will see the complete shape of this polar curve, and in this case, it's a circle. But they're also going to be mindful about the direction in which this polar graph was traced out, as well as the domain that completes the curve. And then your students can use chalk to connect the points, and everyone can then pick up their markers and move to a new location on the concrete to plot the next polar graph B. And then the graph of r equals 9 sine theta in part B has some surprises. Just like in part A, it'll trace out a circle, but it does so on the interval 0 to pi, not 0 to 2 pi. So all reference angles greater than pi will have radii that overlap, which means that students who were assigned values of theta that are greater than pi will have to plot their markers directly on top of another one. Essentially, they'll be tracing out 2 circles, overlapping each other. This introduces the idea that domain is something to consider when graphing polar functions. Part C is a bit more complicated than the circles in parts A and B. Here's what the plot of r equals 3 plus 7 cosine theta will look like once all the markers are laid down. The shape of this polar curve might be hard for your students to visualize at first, but once they are ready to connect the markers with chalk, if they are guided to carefully trace through the 0 to 2 pi markers in numeric order, Then a limmason with an inner and an outer loop will be revealed. The graph from part D of r equals 9 cosine 2 theta reveals a 4-petaled rose. Now, because each of these markers is spaced so far from the previous one, it might be a good idea to instruct your students to trace out this curve with chalk as they're plotting the points in real time. Also, notice how this curve has a stack of 4 markers that coincide at the pole. The next lesson, 9.4.2, starts with problem 9-116, where students create tables of data for 3 different polar curves and then use those tables to sketch graphs on their polar grid paper. Notice that this is the exact same process that the whole class used the previous day in problem 9-105 when they walked polar curves. Eventually, your students will learn to recognize the parent forms of these functions and will know what the parameters do to the shape of the curve. So they're not always going to need to make tables in order to sketch graphs. In fact, the next lesson, lesson 9.4.3, will be dedicated to developing these shortcuts. Problem 9-117 is an interesting problem. Students will use their graphing calculators to reveal the polar forms of samples of each of the 4 conic sections. They will note that some of these polar equations look simpler than their corresponding rectilinear equations, like the equation of the circle in part C, while others, like the parabola and the hyperbola, look much more complicated. Then, running with the fact that your students just discovered that r equals 4 over sine theta is equivalent to y equals 4, problem 9-118 uses that equivalency as a model to walk your students through how to convert a polar equation into its rectilinear form. In part A, your students will cross-multiply the polar equation to find a new equation, r sine theta equals 4, and part B directs them towards a unit circle to show that r sine theta is also equal to y, which explains why y must equal 4. Following that train of thought, problem 9-119 has teams use 3 basic trigonometric relationships: x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared to convert 4 more equations into or out of polar form. Lesson 9.4.3 is a 2-day lesson. During the first day, students will prepare a presentation for their class, and the second day, they will present and take notes on each other's presentations. They'll take those notes on resource page 9.4.3. Now, on the first day, assign each team a different polar function in which to investigate. The options are listed in problem 9-128. Notice that these parent functions are written in generic form, revealing parameters A and B. Students will work with their teams to prepare a detailed presentation for the class regarding the effect that each parameter has on the shape of the graph. This list of bulleted questions will help guide their investigation. The next day, students will present their findings to the class. And as they present, their classmates will take notes on resource page 9.4.3. These notes should be kept with the students, as they are a useful reference guide to use during future review and preview problems, and definitely throughout Chapter 11 when we return to polar functions, only we start applying calculus to them. This concludes our MathCast on section 9.4 on polar curves from a pre-calculus perspective. Calculus will be applied to polar curves in Chapter 11, sections 11.1 and 11.4.